Good day, my dear students. My name is Dr. KK Princess. I am here to present physics subject to SS1, and the topic we are looking at today is elastic properties of a solid. Now, the objectives by the end of this lesson, the student should be able to define and explain elasticity. Number 2, state and explain Hooke's law. Number 3, define and explain tensile stress and tensile strain. And number 4, solve simple calculations on the topic. Now here we go into the topic. The elastic nature of a solid is known as elasticity. Now let us define what is that elasticity as a word. Elasticity is the ability of a substance to regain its original shape and size after being distorted by an external force. For example, when you stretch a piece of rubber band, it will stretch, and when you release it, it will snap back to its original shape and size. Number 2 example, when you attach a load to a coil spring, it will be dangling, but immediately that load will extend the length of the coil spring. But immediately you remove it, the spring also goes back to its original shape and size. Now, and so many other examples. Then, what do we mean by an elastic material? We said here that an elastic material is the material that regains its original shape and size after the distorting force has been removed. When you have removed the distorting force, if that material is able to recall back to the original shape, you now say that that substance is an elastic material. Now let us look at Hooke's law. What does this law state? This states that provided the elastic limit of an elastic material is not exceeded, the extension E of the material is directly proportional to the load or applied force F. Mathematically, you have F is directly proportional to E. Having known the symbols, the meaning F is force and E is extension. Hence, when you remove the sign of proportionality, you put a constant K. And what is that K? K is a constant of proportionality called elastic constant or a force constant, or you can call it stiffness. It has up to 3 names. Stiffness of the material. And this stiffness can be given as K equals F over E, because you got it by making it the subject of the formula from the above expression of F equals K E. Now, what is actually the definition of this elastic constant, which we call stiffness? It is the force required to give unit extension. The force required to give unit extension. Graphical representation of Hooke's law. Number 1, graph of extension E against load L. When you plot the graph of extension against load from the origin 0, 0, it will give you a straight line graph. Then graph number 2, graph of E, that is extension versus load, up to breaking point, because that first one did not reach up to breaking point. It it has not exceeded the limit. So that's why it stopped like that. But this number 2 gets up to the breaking point. Now you see the graph, straight line as you are dragging that elastic material to a particular point. That point, the material can no longer follow you along. It started deforming, deformation started up to breaking point. Then graph number 3, the same thing. This one is load against extension. Starting from the origin, you see the straight line. Immediately it gets there, you keep on mounting pressure on that elastic material. It started giving other shapes that cannot return back to its original shape. Now, let us know the meaning of all the symbols on the graph. I say where P is proportionality limit. This point is proportionality limit, the same thing as on the other one. E, elastic limit. E, elastic limit. Remember we said that once the elastic limit is exceeded, it can break and it will not return back to its original shape. Now, Y is the yield point. You kept dragging this material until this point Y, yield point, it yielded to a break off because it cannot come back again. Now OE, from the origin OE, the whole graph there is elastic region. That's the only place as you are dragging it, it keeps on following you until once you pass there, it will scatter. Then EB, point E, B is showing plastic region. There, you can't return it back again. It's now like plastic. It's no more elastic. Now point B is the breaking point. It will just cut off. So that's about the diagram representation of Hooke's law. Now we come to tensile strain and tensile stress. What is tensile strain? We said it is the ratio of the extension to original length. Mathematically, it is E over L, and it has no unit. That is why I put my no in capital and underline it. After calculation, if you are calculating tensile strain and at the end of the answer you put any unit, you will be penalized for that because it has no unit. Why? Why is there no unit there? Extension is talking about length, L is talking about length, and the fundamental unit of length is meters. Fundamental unit of this one, meters. So meter and meter will cancel off, then there will be no unit. Now tensile stress is the ratio of the force to the area, that is F over A. The unit for this one is Newton meter per second. Why is it Newton meter per second? Force unit is a Newton and the area is in square, in square, that is meters, because area has to do with length. So it is a meter per second. Now from this very stress and the strain, Hooke's law can now be restated in another version, which means if you are stating Hooke's law, it's either you use the first one or you can use this second one. It is the same thing. So from here, it says Hooke's law also states that stress is proportional to strain, provided elastic limit is not exceeded. That is the condition. Even in the first one, there was condition there. If the elastic limit is not exceeded, this one cannot take place. Now, mathematically, we have stress. This is stress formula F over A, directly proportional to strain E over L. Now, when you remove the sign of proportionality to equality sign, you put a constant y. That y is called Young modulus, and the unit of Young modulus is Newton per second square. It has the same unit with tensile stress. Let me stress this point. If you are asked to define tensile stress, or if you are asked to define tensile stress without that tensile, if you are defining this without tensile, you will not score anything. We don't say stress against strain. Tensile is very important. It's a key word there. So the Young modulus, as we have discussed, is given by tensile stress over tensile strain. That's the mathematical formula. Now, let's go over to calculation on how to make use of all those the formulas we have stated above. Question number 1 says, a spiral spring extends from a length of 10.00 cm to 10.01 cm when a force of 20 newtons is applied on it. Calculate the force constant of the spring. Now you look at the calculation critically and then come out with the solution. For the solution, bring out all the information given to you in the question. Extension was given to be 10.01 and 10.00. So you subtract 10.00 from 10.01, and the unit is in cm, which you have to convert to meters. So the difference is now 0.01. Converting it to meters, multiplying it by 100, you convert it to meters, automatically you have 1.0 meters. Without that, you cannot tackle this calculation because Newton is there. You cannot merge cm and Newton. So you always merge Newton and meters. That is why you have to convert it. So having converted it to meters, you quote our formula, the mathematical formula F equals KE. K, make it the subject of the formula. You have F over E, because what we are asked to calculate is force constant, which is K. Now do your substitution into that formula. F is 20 from the question. Force is 20 newtons. Extension is 1.0, as we have seen, and that will now give us 20 newtons per meter. Or if you want to put it in standard form, you write 2.0 times 10 Newton per meter. So that's the solution to that question number 1. Now question number 2. A force of 40 newtons is applied at the free end of a wire fixed at one end to produce an extension of 0.24 millimeter. If the original length and diameter of the wire are 3 meters and 2.0 millimeter respectively, calculate the Roman figure 1, stress, on the wire, strain in the wire. Take pi to be 3.14. As usual, you write out solution, bring out all the things given to you. Force is given to be 40 newtons. Extension is given to be 0.24 millimeter, which you have to convert to meters in order to work with newtons. You convert it by dividing that 0.24 by 1000. You convert it and you have this from the conversion. Now the length is given 3 meters. It's already in meters, so that one has no problem. Then the diameter, they said the 2.0 millimeter. From diameter we can get radius. Just divide the diameter by 2, you have your radius, still in millimeter, which you have to convert to meters, as you have seen on the board. Now, that is preamble, the first step you will do before you can tackle the question. Now, question number 1 says to calculate stress on the wire. Stress on the wire, quote the formula. F over A being the area. Now, area is not given directly here, but we know that the area of a circle is pi r squared, because the wire we're talking about, it has a circular surface. So the area of that circular surface is pi r squared. From there, you do your substitution. F, you have it 40. Pi is given to you to be 3.14. Then radius 1.0 times 10 to the power minus 3 squared, because it's squared there. By the time you simplify this with your calculator, you will get this answer. And the unit is a Newton per meter squared. Now, strain in the wire. You quote the formula E over L. Do your substitution. We know E from our set out. We know E. Divide by 3. Play with your calculator there, and then you get the answer. Remember, strain has no unit. If you attach any unit here, you will score 0, capital letter. That's the examples. Now, look at the assignment here. Assignment number 1. A force of 2 newtons stretches an elastic material by 30 millimeters. What additional force will stretch the material 35 millimeters? Question mark. Assume that the elastic limit is not exceeded. You can see the double units there. So you do the needful by converting the millimeter to work with newtons. Number 2, a wire of length 5.0 meters and the diameter 2.0 millimeter extends by 0.25 mm when a force of 50 newtons was used to stretch it from its end. Calculate. Number 1, Roman figure 1, the stress on the stress. So Roman figure 1, the stress on the wire. Roman figure 2, the strain in the wire. Take pi to be 3.142. Thank you for listening. That's the end of this class. Stay safe. Amen. Please submit the assignment to this email address on the board. Thank you so much.